This is a more realistic projectile motion question. The ones we did in grade 11, everything had to be launched horizontally. That's a little bit silly. In the real world, things are going to get thrown or kicked or launched on an angle. So this matches up more nicely with what we see. We've got something thrown 60 degrees above the horizontal. If you did projectile 3, the rocket going upward, throwing a ball sideways, that got us through, but it's not really how things would be worded. It'd be more worded like this: something's launched on a funny angle. So for this one, I'm always going to doodle a little picture. We've got a golf ball. Oops, that's not a golf ball. We've got a golf ball, little spots on it, let's say. It gets launched at a 60-degree angle and 25 meters per second. So the 60 fits in there. The 25 meters per second fits over here. It follows a parabola. The way this one's worded, the ground must have a bit of a slope to it. When it lands on the ground, it's 2 meters lower than where it started. So a little bit messy, but there's my little picture. Our method for solving it is going to be the same as we did before. Doodle a little picture. Think about what the question asks for. In this case, where it landed. So that's a horizontal distance. And then always start with the other component. What makes this one a little bit different is we're going to have to do components to figure out the V1 and the V2. It's going upward, however fast that side of the triangle is, and it's going sideways, however fast that side of the triangle is. In the rocket question, we knew how fast it was going up and how fast it was going sideways. In this question, we have to do a little bit of work first. If we think about the vertical component, starting with the vertical because the question mark's in the horizontal, if I was standing way off to the side, if I was standing way over here watching this, I might lose fact of the fact that the golf ball was coming towards me. I would just see the ball start to fly upward. Gravity would slow it downward. It would stop at its highest point, and then gravity would turn around and bring it back down until it eventually crashed into the ground. That first split second it was hit, I wouldn't see the ball moving 25 meters per second. I would see it moving that component that I've drawn in purple, that side that's opposite the angle. That's how quick I would see it moving upward. From trig, you can do a little work in the margins to double check. That's a sine relationship. So V1 will be 25 multiplied by the sine of 60. Sine is opposite over hypotenuse, so it is going to be the V that I'm looking for. So V1 all over the hypotenuse, which was 25. So V1 is 25 sine 60. We'll need a number for that eventually. I'm getting that to be 21.65. The A was 9.8. It doesn't say anything about this being on the moon or anything weird. The D value is 2. And as always in projectile motion, I'm curious about the time. The new step that's important that we can't miss is we need to think about directions. The 25 sine 60, it was hit upward, but gravity's pulling it down, and it ended up lower than it started. So sine-wise, the 25 sine 60 has to have a different sign than the A and the D. The 25 sine 60 was up, the A and the D are both down. They gotta have a different sign. So I'm choosing to make down negative again. It doesn't really matter which way you set it up. It might make more sense to make that 25 sine 60 the negative one, and then I'd have two positive numbers. Doesn't really matter. Once we crunch it into the quadratic formula, we'll agree on our 2 times, however we set it up. As usual, we're looking for time, don't care about V2, so we're using that same equation that we've used very often in projectile motion. Crunching in our numbers, -2 equals positive 2165 times t plus 1/2 of negative 9.8 t squared. When I put that in standard form, I get a 4.9 t squared. Flipping the 2165 and negative 2165 times t, the 2 is already there, negative, equals 0. Because we got the technology, I'm going to solve this one a different way. It's a quadratic equation, so you could jump into the quadratic formula. You could have an app on your phone. I'm going to switch and do this with Desmos. With Desmos, I can just plug in my equation. Instead of t, it's the letter y, sorry. Instead of, I'm going to use y instead of d. So y equals, my a term was 4.9. I'm going to call it x squared minus 21.65 x. My c was minus 2. I want to know the roots of that equation. I want to know where it crosses the axis. I want to know when time was 0, but instead of time, I've got y. In Desmos, once we've got the graph, if you touch it, bring back those points. It's labeling the 3 intercepts in this case, the 2 x-intercepts and the 1 y-intercept. Bring them back. Come on, Apple. There we go. Now if I tap the intercept, it tells me the exact points. So one of the intercepts, one of the times I'm looking for is 4.51, I'm going to call it. And the other one is negative 0.91. I don't care about the negative. I'm going to carry the positive one forward. If you just wanted to do this part on with the quadratic formula, that's okay too. But either way you do it, we should agree that after doing the math, delta t is roughly 4.51 seconds. Don't care about the negative value. Once we're done the vertical, then just like we did before, we're going to plug that into the horizontal. Horizontally, it's not tracking across the ground at 25 meters per second. If there was a drone or some sort of camera really high above this looking down at it, it would see the ball moving across the ground horizontally at whatever this adjacent side of the triangle is. It's another trig thing. The horizontal speed is related to the cosine, so it's going to be 25 multiplied by the cosine of 60. And from our vertical, we know it's in the air for 4.51 seconds. To finish it off, the nice thing about the horizontal, it's always that simple equation. D equals the V multiplied by the T. So multiply those out, I'm getting a distance of 56.4 meters. So a little bit of a different question. The difference to the starting point this time is we had to do components on that angular velocity, find the vertical velocity, find the horizontal velocity, then we can plug those into our components. Whichever component we start with, find time, plug that into the other component to